Today, I'm going to talk about a really cool thing which usually gets skipped over in, first linear algebra courses, and it's definitely something that I didn't learn first of all, and it's, why for a specific eigenvalue can its geometric multiplicity and algebraic multiplicity, which I call AKR for its algebraic multiplicity and JKM for its geometric, why do they not always have to be equal? Why can the algebraic multiplicity be more than the geometric multiplicity of an eigenvalue, but it can't be true the other way around? We know that the geometric multiplicity tells us the number of linearly independent eigenvectors of the matrix. So what does the algebraic multiplicity really represent? We learn how to find it, but actually what does it really mean? What does it tell us? It's actually a deeper meaning than most people think, and this is what we're going to be getting into today. So what is the defining property of an eigenvector? First of all, we're going to go over this really quickly, just to stuff make more sense, but again, I'm assuming everyone already knows this. So the defining property of an eigenvector is this over here, if when applying a matrix to a vector, if this matrix has the same effect as only scaling the vector by a scalar, by a scalar lambda, so just a number, then this vector is said to be an eigenvector, and this value over here is said to be its eigenvalue. So again, if we have a vector v, after we apply a to this vector, the only thing that can happen to v is that it can be stretched, it can become longer, it can become shorter, but it can't be knocked off its span. It has to stay on its span. That is, the defining property of an eigenvector. That is what it means to be an eigenvector. And every eigenvector has to it associated some eigenvalue. And with this equation, first of all, how do we even find every single eigenvalue of these eigenvectors? Well, we find the eigenvalue simply by just subtracting this term from this term. We get av minus lambda v equals 0. Boom. And then we factor out v, so we get a minus I lambda v equals 0. And now can someone tell me why, this I is here? Well, obviously we can't subtract, a scalar quantity from a matrix, so we have to turn this into a matrix too, so we can subtract the matrix from a matrix. But we get this over here, and this is it. This is how we can find every single eigenvalue of a certain matrix. This is going to give us a characteristic polynomial. We change this expression to a minus it, and basically what we have to see is the main trick is, since this is a new matrix, this matrix will send a certain vector to 0. It's going to send its eigenvector to 0, and any matrix which sends a vector to 0 which is not the 0 vector, well, that means its determinant has to be 0. So the determinant of a minus I lambda, if lambda is really an eigenvector of the matrix, well, the determinant has to be 0, because there exists some vectors, the eigenvectors, which are not 0, but this matrix sends them to 0. And this is actually, I went too fast, this is actually what the characteristic polynomial is. So we change lambda to just a value t, and we basically say, we get the characteristic polynomial by saying, the determinant of this has to equal to 0. So this will give us a polynomial, in t, and this basically, the solutions to this polynomial will specifically be all the values of t for which the determinant of this really equals 0. These special values of t we're going to call the eigenvalues of the matrix, lambda 1, lambda 2, however much we have. So this will give us a polynomial. I'm pretty sure you've all seen it before. Let's say if we have a 3 by 3 matrix, let's say its characteristic polynomial is going to look something like 5 minus lambda squared times 3 minus lambda equals 0. Or, instead of lambda here, I could have t, and then, these specific t's will be the lambdas. It doesn't matter. But basically, so, I can have lambda 1, lambda 2 here. This matrix has two eigenvalues. This eigenvalue has, this eigenvalue equals 3, and its power here is just, 1. We don't write it. And this eigenvalue has a value of 5. And its power is 2, which means it solves the equation twice. And these specific numbers, this is what we call the algebraic multiplicities of eigenvalues, or I call them AKR lambda. So these powers here are where the algebraic multiplicity is, and these powers have to add up 2 plus 1, have to add up to 3. They have to add up to n, because again, this will be an nth degree polynomial, because it's an n times n matrix. So that's what the algebraic multiplicity really is. It's just basically the powers of the repeated roots in the characteristic polynomial. But what do they actually represent? What determines the size of this power? Well, you would think it's the number of linearly independent eigenvectors, but that's not the case. The actual reason is a bit more deeper, and it's a bit more subtle than that. So this is what the algebraic multiplicity is. And then we ask ourselves, well, why do we need the geometric multiplicity? Well, it's because the algebraic multiplicity does not tell us how many eigenvectors this specific eigenvalue has. For this, we need to look at the geometric multiplicity. Let me just write it down. I hate spelling things out. Geometric multiplicity. This is what we need, which I call GKM lambda. And this multiplicity actually tells us the number of linearly independent, I don't want to spell this out, eigenvectors, eigenvectors of with, eigenvalue lambda. And how do we find the geometric multiplicity? Well, I'm pretty sure you've also done all this before. We have the equation a minus I lambda v equals 0. Once we know lambda is an eigenvalue, so we want to find all the vectors which this new matrix sends to 0. Basically, we want to look at the kernel of this matrix, because the kernel of any matrix are just is the subspace of your vector space, which your specific matrix sends to 0. Usually in a normal matrix, let's say in a diagonal matrix, the kernel would just be trivial. It would just be the 0 vector. It sends the 0 vector to 0. But here, since we solve this equation such that the determinant of this has to be equal to 0, this means that the kernel cannot be the trivial kernel. It has to send at least one dimension of vectors. So it has to send at least one line of vectors to 0, but it could also send more vectors to 0. So basically the dimensions, the dimension of the kernel is exactly what the geometric multiplicity of the eigenvalue is. And again, I'm pretty sure you've all seen how we can find this. We have a matrix that's like 1 3 5 2 2 3 1 1 1, and then again we just subtract from it the specific eigenvalue, and then if the eigenvalue is 2, we just subtract 2 from the diagonals. Then we look at a general vector ABC, and we want it to be sent to 0. So we have this constraint, we solve this constraint, and then we see what the basis of our kernel is going to be based on this constraint, and we see how many basis vectors we get out of this equation, and these basis vectors are going to be precisely the eigenvectors of this eigenvalue. And now the main question is, why does the geometric and algebraic multiplicity, why can they not be equal? First of all, we can see with this that the geometric multiplicity, or JKM of an eigenvalue, well, it has to be more than or equal to 1. It can't be less than 1, because since the determinant is 0, the kernel of a minus I lambda has to send at least one dimensional vectors to 0. We also know that the algebraic multiplicity of an eigenvalue has to be less than or equal to n. It can't be, if the matrix has only one eigenvalue, then that means its characteristic polynomial will only look like, let's say, 6 minus lambda to the power of n, because the characteristic polynomial has to be an nth degree polynomial, and which means that the algebraic multiplicity of an eigenvalue can at most be n, but if there's more eigenvalues, it has to be less than n, but they're going to add up to n. So these are the constraints we have, and now we first ask ourselves, are they always equal? Well, we're going to see absolutely not. Can the geometric multiplicity of an eigenvalue be greater than the algebraic multiplicity of the eigenvalue? Well, very quickly we can see that no, this can absolutely not be the case. Why exactly? Well, it actually makes a lot of sense. The geometric multiplicity, gives us the number of linearly independent eigenvectors. Spelling stuff out is so annoying. The number of linearly independent eigenvectors, and basically, as soon as we have an eigenvector, as soon as the matrix has an eigenvector, well then if we express the matrix, if one of the basis vectors will be this eigenvector, which we can call v1, if one of the basis vectors is the eigenvector, well then the matrix, in that column is going to look exactly like a diagonal, is going to be diagonal with the eigenvalue of the matrix in the diagonal. The easiest thing to see this is for a diagonal matrix, so for a matrix, let's say, which is diagonalizable, which has all eigenvalues on its diagonal, well, it's going to look like this. These will be the eigenvalues of the eigenvectors. This is the matrix expressed in its diagonal form in the eigenbasis. And then the algebraic multiplicity, well, that is just an equation. That is just a polynomial, which is the determinant of this matrix minus it. And we have to solve this for the t's that this equals 0. So if this is our matrix A, then we just subtract t from all these lambdas, lambda minus t, lambda minus t, lambda minus t. And we want this to be equal to, we want the determinant of this to be equal to 0. The determinant of a diagonal matrix is just the product of all the diagonals, so it's just going to be lambda minus t times lambda minus t, all over, and that has to equal 0. So we're going to see that, the solutions are exactly, t, if these eigenvalues are all the same, they're going to group together. So it's going to be lambda minus t to the power of n has to equal 0, and these t's, when t equals lambda, this will be equal to 0. So we can see that as soon as we have a new eigenvector in our matrix, that means if we have a new eigenvector, we have a new term in the diagonal. So when we take the determinant of this factor over here, it multiplies. It's part of the determinant. We just multiply the diagonals together. So we can't. The algebraic multiplicity will always just be. It will depend on the amount of vectors we have in the diagonal, and a new eigenvector will always add something to the diagonal. So the geometric multiplicity physically cannot be bigger than the algebraic multiplicity. It just doesn't make sense. But now we ask ourselves, can the algebraic multiplicity, so can the algebraic multiplicity of an eigenvalue be greater than its geometric multiplicity? And here, the surprising answer is yes, it absolutely can. And this is actually really weird. So, geometric multiplicity tells us the number of linearly independent eigenvectors. Well, what does the algebraic multiplicity tell us? Because, eigenvectors, the more eigenvectors we have, so the higher this term is, well, then the higher this term will be too. But there has to be another special type of vectors which, increase the algebraic multiplicity, but they are not eigenvectors because they don't increase the geometric multiplicity. And that is really weird. That's a really interesting question. What are these special type of vectors? How is this possible? Well, the main answer is, what does the algebraic multiplicity really represent? What increases it? So for the short answer, we can look at, and again, another thing I can mention, which I'm pretty sure, every linear algebra student knows, if the algebraic multiplicity of, every eigenvalue in the matrix equals its geometric multiplicity, then, we know that the matrix is diagonal. We can express the matrix in a diagonal form, but as soon as the algebraic multiplicity for some eigenvalue is more than the geometric one, then, then we don't have enough linearly independent eigenvectors, and the matrix will not be diagonal. And, this obviously makes sense. Because this gives us an nth degree polynomial. So if these values are always equal, then we also have n linearly independent eigenvectors. Basically, what is the short answer? What does algebraic multiplicity really count? Well, to answer this, we have to first look back at our eigenvalue definition, which is exactly AV equals lambda v. Let me just delete this over here. And once we put this on the other side, once we subtracted this, we got that A minus I lambda v equals 0. So to be an eigenvector, it means to be inside of the kernel. If v is an eigenvector, I can express it like this. If v is an eigenvector, then v has to be inside of the kernel of A minus I lambda, where lambda is that eigenvector's eigenvalue. They're such similar words, it's actually terrible. But yeah, this is what it means to be an eigenvector. Now, algebraic multiplicity counts the number, AKR, of an eigenvalue, counts the number of generalized eigenvectors. So what is a generalized eigenvector? Oh my goodness. Well, this is a new term which, some people don't even know. A generalized eigenvector is a vector which is inside of the kernel of A minus I lambda to the power of some value k. Oh my goodness, that is crazy. So an eigenvector with eigenvalue lambda is inside of the kernel of A minus I lambda, but a generalized eigenvector is inside of the kernel of A minus I lambda, the same lambda, but to some power k, where k is less than or equal to the algebraic multiplicity of this eigenvalue. Wow, this is crazy. Oh my goodness, how does this work? Well, this is this is pretty crazy. We have to unpack this slowly. But basically, each eigenvalue has its eigenspace E lambda, and that would just be the kernel A minus I lambda. But each eigenvector has also to it associated a bigger space. E lambda is a subspace of this bigger space G lambda, and we call this the generalized with the S or Z eigenspace. And the generalized eigenspace would just be the kernel of A minus I lambda to some power of k. We can have it to the power of the algebraic multiplicity. As soon as we start increasing the power beyond that, the kernel will not grow. But the generalized eigenspace, generally, they can be equal, or the generalized eigenspace can be bigger than the actual eigenspace of an eigenvalue. So how can we see this? First of all, the first thing I kind of want to answer is, how can the generalized eigenspace even be bigger? Why don't they have to be equal? How does this even work? Well, to look at this, we're gonna call A minus I lambda, we're going to call this whole thing n. This is just a matrix, and we're going to represent this matrix as n. And now again, if v is an eigenvector, that means n sends v to 0, because v is in the kernel of A minus I lambda. So that is all well. But now, what about n squared? Let's look at n squared. Well, n squared, if we apply v to n squared, that's the same thing as saying n, times nv. And again, n sends v to 0, so this is just the same thing as n 0, and that just is 0, because every matrix sends a 0 vector to 0, which means if v is in the kernel of A minus I lambda, then it will also be in the kernel of A minus I lambda to the power of k, which means the eigenspace is a subspace of the generalized eigenspace. But notice that this space can actually be bigger than just this n squared can send more vectors to 0 than just n. And we can see that by saying, let's look at n squared x, where x is just a random vector which is not an eigenvector. So x, we're gonna say is not inside of the kernel of a minus I lambda. Well, let's see what happens. N squared x, that's the same thing as saying n times nx, and let's say that n now sends this vector x to our vector v. Let's say that nx, this sends x to our eigenvector v. Well, then this would be the same thing as saying nv, and n sends our eigenvector v to the zero vector. So all of a sudden we saw that the kernel just grew. And n squared still sends all our eigenvectors to zero, but it can also send other vectors. For example, x. If n specifically sends this vector to our eigenvector, then it will also be sent to zero. So x is in the kernel of this space. And basically, what we say is that x is a rank 2 generalized. Am I spelling this correctly? Rank 2 generalized eigenvector. And our actual eigenvector v is just going to be a rank 1 generalized eigenvector. I'll just call it GE. Oh yeah, that's so tough. Rank 1 generalized eigenvector. So basically, all eigenvectors are rank 1 generalized eigenvectors, and all higher rank eigenvectors are eigenvectors which get sent to zero after applying a certain power. If we have a different vector, let's say y, and if we have a minus I lambda y cubed equals 0, but a minus I lambda squared y does not equal 0, well then we know that y is a rank 3 generalized eigenvector. Because again, if we put it to the power of 4, it would also be sent to 0. What matters is the maximum power, or let's say the minimum power where y still gets sent to 0. That tells us the rank of a generalized eigenvector. And this is pretty crazy. This is wild. And now again, we can also see, if we just, let's say, imagine a 3x3 matrix, with its three-dimensional space. Let's say that in this space, let's say this matrix has one eigenvector, lambda 1, and this eigenvector has an algebraic multiplicity of lambda 1 equals 2, but the geometric multiplicity of this value lambda 1 equals only 1. Well, what does that mean? That means that this matrix will send a specific 1D line of vectors. This will be the eigenspace of this eigenvalue, and it's going to send a specific 1D line of vectors into the zero vector. This will be, because geometric multiplicity is 1, means there's only one, a one-dimensional eigenspace. But since the algebraic multiplicity equals 2, we know that there has to exist some sort of plane. There has to exist some sort of two-dimensional plane where every single other, where this line lies on the plane, but every single other vector which is in the plane but not on this line, well, every single one of those vectors will be a generalized eigenvector of rank 2, which means any vector which I have on the line here, after I apply a minus I lambda to it, this vector is going to fall onto this line here, and then when we apply a minus I lambda to it again, it's going to go to 0. So this plane over here, this is the generalized eigenspace. And again, there is a theorem telling us that basically the direct sum of all of these generalized eigenspaces of a matrix, exactly gives us the whole subspace of our matrix, the whole n-dimensional subspace, let's say Rn. But it has to be, this only works under an algebraically closed field, so I'm going to have to say Cn, there's just a small detail. But basically, these spaces, they kind of form well in algebraically closed field, which means we have to work over the complex numbers. Don't worry about that too much right now. Basically, this is this now you kind of have a small intuition about eigenvectors. And another thing, another thing that I kind of want to talk about right now, like going deeper into generalized eigenvectors, is let's actually see their properties a bit more, because again, we still don't really know why generalized eigenvectors are counted in the characteristic polynomial. Why does the algebraic multiplicity still count these generalized eigenvectors? Why do they still increase the algebraic multiplicity? Well, let's go a bit deeper into them. We're going to see that all higher rank generalized eigenvectors decompose into lower rank generalized eigenvectors. So let's say we have an eigenvalue, and then this, well, I drew it so terribly. Let's say we have an eigenvalue, and let's say its algebraic multiplicity is going to be 3, but its geometric multiplicity is only going to be 1. Well, then we know that this matrix has an eigenvector v1, but it will also have two higher rank generalized eigenvectors. So it's going to have a rank 2 generalized eigenvector and a rank 3 generalized eigenvector. So I'm just going to write them as v2 and v3. Well, then a very cool property is that a minus I lambda of v3 will equal v2. So v3, we're going to see that it's not always this simple. I'm going to explain this in a second, but basically v3 decomposes into a lower rank generalized eigenvector after applying a minus I lambda. And again, if we apply a minus I lambda to v2 now, it's going to decompose into v1. And then again, if we apply a minus I lambda to v1, well, we know this is the defining property of an eigenvector. It has to be in this kernel, so this has to be sent to 0. So we see that a minus I lambda cubed of v3 is going to be 0, which is why v3 is a rank 3 generalized eigenvector. But if this wasn't cubed, if this was only squared, well, then we see that this would not be equal to 0. This would be equal to v1. So this is how higher rank generalized eigenvectors work. They decompose into one another, and this kind of makes sense, because eventually, once we, if we have let's say if we have a rank 3 generalized eigenvector, once we apply, again, we can just call a minus I lambda n. Once we apply n to it, we get a different vector. We get a different vector, and then we apply n to it again, and we get a different vector yet again. And then at the end of its rank, when we apply n to this final vector, we can just call v. We know that has to equal 0. But, any vector that n sends to 0 has to be an eigenvector. So we know that no matter how high rank the generalized eigenvector is, eventually, after applying a minus I lambda to it enough, we have to, it has to turn into the eigenvector, because then the next application of n is going to be the one which sends it to 0. So basically, all higher rank generalized eigenvectors will eventually turn into the real eigenvector after applying this, which is kind of cool, and this is kind of how it makes sense when we think about this. And now another cool thing, just which we notice, is that looking at this equation over here, let's put this, let's multiply v out and put it on the other side. We see that a v2 equals lambda v2 plus v1. So basically, v2, a rank 3 generalized eigenvector, it acts like an eigenvector. A v2 equals lambda v2. This is the proper behavior of an eigenvector, plus v1, so plus a shift term. Generalized eigenvectors act like eigenvectors plus a little shift term, and we see that this shift term, this generalized eigenvector shifts directly in the direction of the actual eigenvector of this specific eigenvalue lambda. So basically, a property that we see is that all generalized eigenvectors, after a while, they shift towards the direction of the actual eigenvector. So if we have an actual eigenvector, if we're in our generalized, subspace right now, or in the generalized subspace of this of a specific eigenvalue, well then if we have some generalized eigenvectors here, after applying a to them enough times, they're kind of going to grow, but they're also going to shift towards the direction of v, which is the actual direction, which is the actual eigenspace inside of this generalized eigenspace. And again, we can kind of see this. Let's say we apply a to this again. Well, if we apply a to this again, a lambda v2 plus v1, well, we see that a, again, it's going to scale v2, but it's also going to turn v2 into v1, and how a is going to act on v1, well, a v1 just equals lambda v1. So, each time we apply this again, all these v2s are going to turn into v1, and, it's all going to start scaling, but, there's going to be more and more v1s in the equation. So basically, this rank 2 generalized eigenvector, after applying, if we apply a to the power of 100 to it, it's going to be acting more and more just like, the actual eigenvector v1. So this is a slightly cool property. But now the final thing I really want to talk about is, kind of the most important thing is the Jordan normal form. And this is what really closes the story, Jordan normal form. So if you survived for this long, this basically tells us that every single matrix can be written as an almost diagonal matrix. And what I mean by an almost diagonal matrix means that, it's a diagonal matrix, with the eigenvalues on the diagonal plus some ones on the super diagonal, which is the diagonal right above the diagonal. And that's it. Everything else are zeros. And this will be very important. Basically, the first thing I want to mention is, before when I said that, a minus I lambda of, let's say we have a higher ranked generalized eigenvector, like a rank 3 generalized eigenvector, v3, well, after we apply a minus I lambda to it, it doesn't necessarily have to go to v2. It can go to 7 v2 plus 5 v1. It decomposes into lower rank, generalized eigenvectors, but, it can also decompose into a linear combination of them. But we can always specifically pick, remember, generalized eigenvectors, for an eigenvector, it has to be specifically on this line over here. But, in the eigenspace, generalized eigenvectors can be anything inside of the generalized eigenspace. So, there's an infinite amount of them. We can pick a bunch of them. We can always pick such generalized eigenvectors such that they decompose nicely into their constituent, lower rank eigenvector parts. So basically, a minus I lambda v3 can equal v2. We can always pick such generalized eigenvectors such that this is the case. And then in that basis of eigenvectors and generalized eigenvectors, which decompose nicely into one another, in that basis the matrix can look almost diagonal. And under an algebraically closed field, any matrix can look like this. So only some matrices can be diagonal, but every single matrix can be diagonal with only some ones above it on the upper diagonal. And then again, these ones also make a lot of sense, and I'm gonna explain it in a second. So basically, this is a Jordan normal form of a matrix, and basically this will make the most sense, and it's going to close the whole story with a small tiny example first of all. So let's say we have an n by n matrix, and let's say it has an eigenvalue, and let's say this eigenvalue has an algebraic multiplicity equal to 3, and it has a geometric multiplicity equal to 1. Well, then we know that this eigenvalue has an actual eigenvector v1, and it also has two higher rank generalized eigenvectors, so v2 and v3. Now, first of all, how do we find v3? How do we find, we can find v1, just simply, we already know how to find it with our old processes. So we can find v3 by saying a minus I lambda cubed v3 equals 0, and then we can also say a minus I lambda squared v3 does not equal 0. And then with these sets of equations, it's usually enough that we can actually find our specific Jordan normal form generalized eigenvector. And then again, we can say now that a minus I lambda v3 equals v2, and we can find the lower rank generalized eigenvector. And then we can also demand, if we don't have enough equations, a minus I lambda v2 equals v1, where v1 we can find. And, in this specific basis, then let's say our matrix, our n by n matrix will exactly have these eigenvalues in the diagonal, but it's gonna have ones on top of all the generalized eigenvectors. So this is an eigenvector, it has no 1 over, but these two are generalized eigenvectors, so they have a 1 over them. And, then everything else. And if we imagine that we only had a 3 by 3 matrix, where it only has one eigenvalue, with then this 3 by 3 matrix would look, I can write it a bit nicer. This 3 by 3 matrix would look exactly like this. It would have lambdas on the diagonal, it would have ones on the super diagonal, and everything else are zeros. So this can very much happen, and we can turn using this Jordan basis, this matrix can look like this. And how do we explain these ones? Well, if you remember what a matrix actually represents, a matrix is always expressed in a specific basis. This time when this matrix looks almost diagonal, the basis vectors are going to be exactly our generalized eigenvectors. In a diagonal matrix, the basis vectors are all the eigenvectors, but here if it can be diagonalized, the basis vectors will be the eigenvectors plus also the higher rank generalized eigenvectors. So, and then the columns of a matrix are just where this linear transformation T, or I'm just gonna say A, where this matrix A sends these vectors. So A v1, A v2, A v3. These are gonna be the actual these are what the columns of the matrix represent. I already made a video about this a while back. But basically that means that v1, where does A send our vector v1? Well, A sends our vector v1 to this vector over here, which is just gonna be lambda times v1. So A sends v1 just to lambda times v1 plus 0 times v2 plus 0 times v3. So a v1 equals lambda v1. We can see this is this is an eigenvector. Eigenvector. Bang, easy. But now where does A send our vector v2? Well, A sends v2 into this vector over here, which is 1 times v1 plus lambda times v2 plus 0 times v3. So it's going to be v1 plus lambda v2. And oh my goodness, this is exactly what a generalized eigenvector is. We see if we subtract v from both sides, a minus I lambda v2, a minus I lambda v2 equals v1. So we can see, literally where v1 is our eigenvector. So we can see that v2 is, a rank 2 generalized eigenvector. And now if we look at where our matrix sends v3, v3 gets sent to this vector over here. So a v3 equals v2 plus lambda v3. And again, by rearranging this, we basically see that a minus I v3 equals v2. So v3 is, again, a generalized eigenvector of rank 3, where then, v2 gets sent to v1 after applying this again. So, this makes great sense. Basically, again, if we look at the vector, for example, if we look at the vector 1, 0, 0, we see that 1, 0, 0 after after multiplying this by all these values over here, we're going to see that we get exactly the vector lambda 0 0. So 1 0 0 is our specific eigenvector, and then a different vector, for example 0 1 0. Well, this is a generalized eigenvector because 0 1 0, again, after multiplying with all these columns, what we're going to get is exactly 1 times v1 plus lambda times v2. So 0 1 0 is exactly a generalized eigenvector. And now for the kicker, what is the algebraic multiplicity? The algebraic multiplicity of an eigenvalue. Well, again, that just depends on the characteristic polynomial, and the characteristic polynomial, is just the determinant over matrix A minus it, for all t's such that this determinant equals 0. So we got to solve this polynomial, for all the t's, and these t's are going to be the exact eigenvalues. And this the determinant doesn't depend on the basis of a matrix. We know that any matrix A can be expressed in this looking way using all its eigenvectors and all its generalized eigenvectors, and expressed in Jordan normal form. Any matrix can look like this, and the determinant of a matrix which is upper triangular, even if it has ones up here, the determinant of an upper triangular matrix, so if there's all zeros in the lower triangle, the determinant is still the product of these diagonals over here. So the determinant of this of A minus it, again, if we have this matrix over here, and if we subtract, if I write this a bit, if we subtract t from all the diagonals, and again we have ones here and then zeros everywhere else, if we subtract these from the diagonal and look at the determinant would just be this product. So it's going to be A minus the determinant will just be, what am I writing? Lambda minus t to the power of 3 in this example over here. Just going to be the product of all these diagonal terms. And then the characteristic, the algebraic multiplicity, is just, the power of our characteristic polynomial. The algebraic multiplicity of a specific eigenvalue will just be the power that, that there is in the characteristic polynomial. That, we can see that doesn't change. For an eigenvector, it will have no ones above it. Generalized, this will be a rank 2 generalized eigenvector. This is a rank 3 generalized eigenvector. The ones here will not change the nature of our characteristic polynomial. It will still look exactly the same, which is why generalized eigenvectors, even though they're not eigenvectors, they still add a multiplicity to our algebraic multiplicity. And this is the whole end to our story. Now we can see that as soon as a matrix doesn't have n linearly independent eigenvectors, as soon as it has some generalized eigenvectors, well, generalized eigenvectors, they have the property that, let's say v2 equals lambda v2 plus some drift term, which is a lower rank, generalized eigenvector. So they're not eigenvectors. It doesn't count. But they still, a matrix can still be made to look upper triangular with them, and so they will still, add in the characteristic polynomial. They will still add a power to the algebraic multiplicity. Bang! That is the end of the video. There's also a nice mathematical way to kind of prove and show why the algebraic multiplicity can be more than the geometric one. It basically mentions the same things as this, but it's a bit more rigorous and well proved. So I can also make a video on that once in the future. But that is it. Thank you for watching. I hope you enjoyed, and goodbye.